On this video, we're going to talk about section 11.4, solving separable differential equations. If you recall from the work we've done earlier, a solution to a differential equation is a function. It has to satisfy the differential equation. That is, if the differential equation it can include many different things, the function itself, y, various derivatives, maybe y prime, maybe y double prime, other expressions as well. So when you plug all those things into the differential equation, it is a true statement. That may be just a general solution if there's some constant c in there. If initial conditions are given, then the function has to also satisfy that. And we just need to remember it's only going to be valid on a continuous domain. So if there's some kind of discontinuity, maybe a vertical asymptote or some undefined point, it will only be valid, the solution will only be valid on that part of the domain that includes the initial condition. So let's work a few examples, and then I think this will help clarify things a little bit. So I'm going to start with the differential equation dy dx is equal to negative x over y. All of the differential equations that we solve in AP Calculus AB will be what are known as separable differential equations. That's a particular kind of differential equation, a class of differential equations. And what makes them separable is that we can separate the variables. We can put all of the x terms on one side of the equal sign that are multiplied by dx, and all the y terms on the side of the dy being multiplied by dy. So I'm going to move the y to the left side by multiplying by y, and simultaneously I'm going to move the dx to the right side by multiplying by dx. So that is going to make it look like y dy on the left and negative x dx on the right. So at this point in time, we have separated the variables. We've got all the y stuff on the left side times dy, all the x stuff on the right side times dx. So now it's safe to multiply both sides of the equal sign. So on the left, when we integrate with respect to y, we're going to get 1/2, let me write that as 1/2 y squared. Now, you could get a plus c, but we're just going to agree to always put the plus c on the side where the x is. So integrating negative x is going to be a negative 1/2 x squared, and then the plus c is going to go on that side. So we're trying to solve this, so we want to find y. So I'm going to multiply through both sides of the equal sign by 2 to get rid of that 1/2. So that's going to lead to y squared on the left, and it's going to become now a negative x squared on the right. And this plus c, the c represents some unknown constant, and since I don't know what it is yet, when I multiply it by 2, it's still an unknown constant, so I'm going to leave it just as this plus c. Now at this point, we have a little bit of choice. There's a few different answers that would be acceptable. We're going to have a hard time solving for y because, as you can see, if we square root both sides, we're going to have to get positive or negative and then get the square root of that negative x squared plus c. And that would be one correct form of the answer. You would have to leave both the plus and minus in there at this point in time, because we don't know which. You can't have both of them because that wouldn't be a function with the plus or minus, but we don't know which one we're going to have to use until we get an initial condition. Alternatively, you could just leave it as we had it, as y squared is negative x squared plus c, or you could also, it might look a little more familiar, if you add the x squared to the left side and write that as x squared plus y squared equals c. So any of those three versions would be acceptable for what we will call the general solution. So it still has that unknown constant c in there. So you can kind of see we're getting from that third version, what we're really looking at is it's a family of circles centered at the origin with some unknown radius at this point. Of course, a full circle would not be a function, so really it's going to have to be a semicircle, and we don't know yet if it's going to be that top half of the semicircle or the bottom. So I'm going to now add an initial condition in here so that we can actually get this a little more conclusively. And sometimes you will not get initial conditions and you'll just be asked to find the general solution. Many times you'll be given initial conditions, which means you have to go further and get more explicitly what is that particular function. So I'm going to say that y is equal to -2 when x is equal to 0. So now we can use any of the versions that we want. I'm going to use the one right here. So we're going to plug in -2 for y. And you can see now that this plus or minus is going to be resolved. Because the y is negative, the only way we can get that negative result is if we choose that negative in front of the radical. And so we're going to get that, if you're thinking geometrically, like you might have seen from here, we're going to get a semicircle that's the bottom half of that semicircle. And then I'm going to plug in the 0 for x, so that's going to be a -0 squared plus c. And so that means we have, at this point, the -2 is equal to square root of c. If we square both sides, we're going to get that 4 is equal to the c. And so that then means that our solution is going to be y equals square root of, and you can either write the -x squared first, just to make it look a little nicer. I'm going to write the +4 for c first, minus the x squared. That is our particular solution. Okay, let's try another example. So I'm going to go to a new screen, and we'll start with the differential equation. Dy dx is going to equal 3y. So we are going to begin again by separating the variables. So we want to move the y to the side with the dy in it. As a general rule, we're going to keep the y side as uncluttered as we can. So I'm going to leave the 3 part on the side where I'm going to put the dx. The only exception to that might be is if it would make this integral on the left side easier. Like if I could bring over something like a 2y so that the integral would be just a nice y squared, I might have done that, but that's just trying to be efficient. So at this point in time, we have separated the variables. So we have 1 over y dy is equal to 3 dx. And so now we can integrate both sides. On the left side, we're going to get the natural log, and we're going to call that the absolute value of y. Again, I'm not going to put the plus c on the y side. On the right side, we're going to get a 3x, and then I'm going to put the constant of integration on that side with the x. So it looks like that. And to solve for y, I'm going to exponentiate both sides. If you want to think of raising both sides as an exponent base e, that's going to give us y. Now, I'm not going to call that absolute value of y now because I'm going to go through this one more time. We talked about this in class. This e to the 3x plus c is going to, if we use property of exponents, that's the same thing as e to the 3x times e to the c. This e to an unknown constant is itself just some constant. And so we get to y equals c e to the 3x. So you're free to jump right to this and not have to do all of these in-between steps along the way. So you're welcome to go straight from what we have here to what we have there. That would be perfectly okay on an AP exam question. So that's now our general solution. So I'm going to add now an initial condition, and I'm going to abbreviate that IC, just trying to be efficient here. I'm going to say y is equal to -5 when x is equal to 0. Now, if I can go back for a moment, when we had this absolute value of y right here, I didn't bother writing that absolute value there, because what the absolute value here would have meant is that this could have been equal to either a positive or a negative number. It couldn't be both, because it wouldn't be a function if it was both. And so the idea is that that option for y being positive or negative is carried in that constant c. So when we now solve for our initial condition, the c is providing us that opportunity to get either a positive or a negative number, or a negative value. And that's what we're going to see in this case, is that when we plug in the -5 and we put in the 0 for the x, it means that c is in fact going to be -5. And so that is going to make our solution, our particular solution, the one that solves the differential equation and the initial conditions both, is going to be y equals -5 e to the 3x. So there's the solution to our differential equation. Okay, let's work another example. And so I'm going to go to a new page here, and this time we're going to start. This is going to be a little bit more challenging. I'm going to call this dp dt, the p trying to suggest maybe this is some kind of population function, and the t maybe suggesting that this might be some kind of, that is with respect to time, so a population growth or decline with respect to time. I'm going to say it's equal to -k times p minus 20. And this isn't really a big deal, but I'm going to say here that k is positive. It's going to be, we'll see many of these down the road, a lot of these kinds of problems, and sometimes that's going to be referred to as the growth constant, or maybe a decay constant, if this population growth is growing exponentially or decreasing or decaying exponentially. So to start with, we're going to separate the variables. This is a much more challenging separation of variables than the others. The question might be, what are you going to do with this -20? And it may be tempting to distribute the -k over there. That's not a good idea. We have to bring, because we have to move this p over to the side where the dp is, we're going to have to bring the -20 with it. There's no way to deal with those independently. So the trick, or the key to doing this problem, is to divide the entire p minus 20 over to the left side to multiply that dp. I would leave this k, this constant, unknown constant for now, k, with the dt on the right side. So now we have separated the variables. This constant, this k, remember, is not a variable, it's just some constant. And so we're now going to integrate both sides, the left side with respect to p and the right side with respect to t. Now, if you like, you can make a u substitution and say the whole denominator is p minus 20, and that would make the du equal to dp. You might be able to do that in your head. Either way is okay. The integral is going to become, if you did the substitution, this integral would become 1 over p dp, which would make that integral be, I'm sorry, 1 over, let me change those, 1 over u, if we're going to make that substitution. So it would be 1 over u du, which would give us the natural log of the absolute value of u. Either way, if you did the u substitution or not, if I didn't do the substitution, we're going to end up in the same place, where we're going to get the natural log of the absolute value of p minus 20 is going to equal the negative kt plus c. Now, as we have done before, with just now a little bit more complicated result, we're going to exponentiate both sides. So when we do that, that will get rid of the natural logarithm. We're not going to worry about the absolute value of p minus 20, but instead just call it p minus 20 and know that we're going to get that c e to the negative kt as our function on the right. So going one more step, adding the 20 to the other side, we're going to get that p is equal to 20 plus c e to the negative kt. So that is our general solution to that differential equation. To solve for c and k, in this case, we would have needed two initial conditions. Since there's two unknowns, we would have to have the information, two different pieces of information to solve for both k and c. Now, just a little visual of what's going on here. If we wanted to see what is happening here, we're going to see that since k is a positive constant, as t gets bigger and bigger, as t goes to infinity, then this e to the kt is going to become e to a very large negative number, which is, so e to a large negative number is the same thing as 1 over e to a large positive number, and that is going to go to 0. So as t gets very, very large in this, say, population model, this ce to the negative t is going to go to 0, and so we're going to get this horizontal asymptote at p equals 20. So that means in the long term, the population is going to approach 20, whatever 20 represents. That might be 20 insects, that might be 20 million ants, or whatever it might be, whatever the population represents. Now, what we will see is that depending on what we find for c being positive or negative, we are going to get these exponential growth curves or reflected exponential growth curves. So if we had an initial condition that gave us a point, say, up here at time 0, we would see something that's going to approach that asymptote of 20 as t gets larger and larger. If our initial condition gave us maybe a population down here, might be kind of hard to get a negative population, so maybe more realistically it might be somewhere here, a smaller positive, then it's going to approach that asymptote from below, something like that, like an exponential growth or decay model that's been reflected, that's been multiplied by a negative. That's kind of the picture going on behind the scenes there. Those are kind of tough differential equations, but they appear fairly regularly. So I'm going to do one more example here. So I'm going to go to a new page, and on this one we're going to start with dp dt again, so looking like a population model perhaps, and then it's going to equal 2p minus 2p times t. And I'm going to start with this, and we'll get the general solution, and then I'm going to add an initial condition. So here we want to separate the variables, but that's not totally obvious at first glance because we've got p's and t's mixed in together there. So our best strategy here is going to be to factor that p out. You could factor a 2 as well, but as I said earlier, generally we want to leave all of the congestion, all the messiness over on the dt side and keep the function side as clean as possible, because we're going to have to eventually solve for that function. So I'm going to divide the p over, making that 1 over p dp. I'm going to leave all that other stuff, the 2 minus 2t, the 2 minus 2t, and then multiply the dt over. And so now we have separated our variables. We'll integrate both sides. So as we've seen many times before already, we're going to get the natural log of the absolute value of p on the left side. On the right side, we're going to do each of those integrals separately. The integral of 2 with respect to t is going to be 2t. The integral of a negative 2t with respect to t is going to be a negative t squared, and then we're going to put our constant of integration on the side with the t's in it. As we have seen before, we're going to do this more quickly and not write all the steps that lead to this, and that's okay. We're going to just call it p, no longer an absolute value, but this plus c here is going to be a c e to the, and then it's 2t minus t squared, all appearing as the exponent. So this is our general solution to the differential equation. So I'm going to add in now some initial conditions so that we'll be able to go a little further. And so I'm going to say in this case that p is equal to 5 when t is equal to 0. So armed with that information, we are going to, with our general solution, we're going to plug in the 5 where the p is, and the c is what we're going to try to find here. And we're going to have e to the, and since t is 0, all that stuff is going to become 0, which means that we're going to get that c is equal to 5. And that means that our solution, our particular solution to the differential equation with the initial conditions is going to be 5e to the 2t minus t squared. So there is, we will call this a particular solution. And hopefully that's enough to get you going.